Hello everyone, and welcome to Litmus Test. I know it's been a little while since my last video. There was a lot of stuff going on, moving apartments, work, etc. But today we're going to continue with our discussion of thermochemistry, and today's goal is to use specific heat, the idea of specific heat, which we talked about in a previous video, to determine how much energy it takes to heat up our metal from room temperature to the melting point. And we want to use this to determine how much heat it takes to melt some of these metals. So again, we're going to use this copper and this charcoal. We stick it in the furnace, and two things have to happen. First, the copper has to get up to the melting point, and then the copper has to melt. Now, these aren't really specified as being different processes in Minecraft, but they are different processes because you have to warm up your stuff before it can melt. And it turns out that once you warm up the stuff, it still takes a little bit of extra energy to convince the atoms to actually melt. So we have all of our metals here, and we have a little book here that tells us all sorts of useful information. I'll show this again at the end of the video. And we have a little roadmap. Now, this roadmap doesn't mean a lot to you right now. Don't panic. We're just going to work at the first two lines, and we're only going to work at this first two lines right here, where it says V plus D goes to M. That's all we got to hear about at the moment. V and D refer to volume and density, and M is mass. Now, we need this because eventually we're going to use some other things with mass, but let's come back to that. Let's just start one thing at a time. Let's look at this sign first. We know that the volume of an ingot is 1/9 of a cubic meter because there are 9 ingots in a block, and a block is a meter cubed. So a volume of an ingot is 1/9 of a cubic meter. And we also know that our dusts, our grit, have the same volume as one ingot. They produce one ingot, so they must have the same volume. We know that 1 meter is 100 centimeters, and I'm going to call that number F for no reason at all, just to save space on the sign. If we take our volume, our 1/9 cubic meter, and divide that by the cube of F, then what we're saying is that we're going to cube this meter, we're going to cube these centimeters, so that way we can get rid of this meter cubed that we have here, and we're going to replace it with centimeters cubed down here. So if you get out your calculators and you plug in 1/9 meter cubed divided by 100 centimeters cubed, you end up with this number. 111,111.111111. If you ever divided 1/9 on a calculator, you'll notice that 1/9 is just 0.111111, etc. So this is just 1/9 times a bunch of centimeters, and this should make some sense. It's 1/9 of a cubic meter, so there's a bunch of ones, and there are a lot of centimeters in a meter. There's even more cubic centimeters in a cubic meter. So this is just saying we have a lot of cubic centimeters as our little v. Okay? So we have a number here for little v. This is the volume of an ingot. Also, the same volume of our copper grit, because remember, 1 copper grit makes 1 ingot. So, now that we have our volume, what next? Well, we're going to take volume and use density to get the mass. Alright? Let's look at our next sign. Density is mass divided by volume. And we can rearrange that a little bit to solve for mass just by multiplying both sides by volume. So we get mass is volume times density. Here we have to look up the density of our copper. So let's look up, and our copper has a density of 8.96. Alright, so with a density of 8.96, in fact we can write that down so we don't forget it, grams per cubic centimeter, what is our mass going to be? Well, go ahead and get out your calculators. Remember that our original number was this bunch of ones in the 100,000. We're just going to multiply that by 8.96, and we're going to get this number. This is a very large number of grams. In kilograms, this is almost 1,000 kilograms, and that comes out to 452 pounds, or just under 452 pounds. So this 1 ingot is really big, and that makes sense. It is, like a meter is like a yard, so it's like 3 feet, and that's 1/9 of cubic 3 foot. It's really big. It weighs like 452 pounds. That's a lot. But now that we have that mass, which is almost 1,000,000 grams, what do we do with it? Well, we say mass plus the molar mass makes the number of moles. Again, we'll come back to our second line, which tells us why we're doing all this. But first, let's just do it first so that we get it out of our heads. We looked up the molar mass of our copper in our little thing here. It's at the end. Molar mass, copper, is 63.55, sometimes 63.56, depending on how you round, grams per mole. And we know that the molar mass is just grams per mole, or mass over number of moles. So we can say that the number of moles, if we just multiply both sides by n, we can figure out what this is. So is this correct? Multiply both sides by m. Not, it's actually divided by. There we go, because we multiply both sides by n, so we get nw equals m. And then we divide by the w, so that we have n equals m over w. So let's plug those numbers in. We take the number of mass we had just a few screens ago, and we take this molar weight that we have now, and figure out how many moles do we have. So we've got that 995,000. We're just going to divide by our molar mass, 63.56. And if you've all done this along with me at home, then you get 15,663.24 moles. In fact, I might have room to put a comma there. There we go. 15,663 moles. That tells us how many atoms are in our one ingot. Now, why do we care about that? That's where we look at this third line. The second line says that we can use the number of moles, the specific heat, and the melting point to figure out a change in enthalpy, or in other words, an amount of heat. And that's the amount of heat that we're going to use to get to the melting point. I have this equation here, Q equals NC delta T. This says the heat, Q, is equal to a number of moles times the specific heat times the change in temperature. Change in temperature from room temperature to the melting point. Let's calculate that real quick, because we have N, and we can look up our specific heat, C, right here, 24.44. We know that the melting point of copper is this 13,000. We saw that last video in our giant tower of melting points. And again, we can look it up here. And we know that room temperature is this 293. So all we have to do is subtract this to get the amount of degrees that we're going up. So 1357, 7, of course, don't forget that, minus the 293. And we end up with almost 1,000, a little over 1,000 Kelvin. So we have 1,000 degrees to go to warm up our copper from room temperature till it gets to the melting point. So if we take all of these numbers and we plug them in, we're going to take that N, which is, as you can see off to the side, the 15,663.24. We're going to take that C, which is the 24.44, and we're going to take that delta T, which was the 1,064.62. 64.62. And if we plug all those in together, we get a very, very large number. That's a very big number. So we have our number of moles, we have our specific heat, and we have the delta T. And we get this many joules. This is a very, very large number. In fact, if we look at this, we have 1, 2, 3, 4, 5, 6, 7, 8, 9 decimal places there. So we can abbreviate this a little bit. Which would just be about that many, kilojoules, like this. So that many kilojoules. So this is a massive, massive number of a massive amount of energy, right? We've got millions of joules, millions of kilojoules, Just huge. It's actually a billion joules and millions of kilojoules here. Just absolutely big. What does that mean in terms of like everyday life? Well, it means that you probably can't melt copper very easily at home. It means you need a really good fire to do it. And if you ever look up people on YouTube who are melting things, they've got very hot very hot flames and forges to melt metals. It's not an easy task and something that takes a little bit of time. So that's one hint as to how much energy is in charcoal. However, in terms of like actual modern infrastructure, this amount of energy isn't actually that huge. I mean, we can melt copper and steel and all the time, and we produce lots and lots of energy through burning coal, oil, through solar, natural gas, and through wind. We get megajoules regularly, and in terms of megajoules, this is only like a couple thousand megajoules, maybe 10,000 megajoules. This is something that was easily obtainable by most steel mills and other foundries and most power plants. It's megajoules, but that's no big deal. Not something you're going to get at home. So that's how much energy it takes to raise copper from room temperature to the melting point. Your homework for today is to go through, and I'm going to let you screenshot these. Here's the table of densities and specific heats, melting points, and molar masses. Now that you've seen how to do these calculations, work through these other metals and come up with some numbers that say how much energy is it going to take to melt or to get each of these metals to the melting point. Next time, we're going to talk about how to melt them and how to rank them from best to worst, etc., to figure out how much energy is in a piece of charcoal. So until next time, stay safe and don't catch on fire.